All right, so far what we've done is we've developed this way of really dealing with differential equations that can be useful in different things, circuits and all those things. But one of the interesting things that happens in differential equations, and it's important to note, it's a rather short note for us, but for the sake of completion, is how you deal with initial conditions. Because so far we haven't been really explicitly dealing with initial conditions, right? So the question is that, and the way we've been kind of avoiding that is that we've been dealing with one-sided functions, essentially, right? So because we have all these u's of t's in the system. Now let's say you have a two-sided function, y of t, which is two-sided. So we're talking about the initial conditions. Now let's say you have y of t that's two-sided. And let's say you're interested in understanding how to deal with it as a differential equation. Right? So now I define a new function, y plus of t, which is one-sided. Essentially, it's y of t times u of t. I multiply it by u of t. I just look at only the right-hand side of it, the positive side of it. So this y plus of t is a one-sided function. Now, I can also now I can calculate two things. And it may seem a little bit random initially, why am I doing this? But you will see why it's useful in a second. So let's imagine that I can calculate the derivative of this function. Essentially, I show it with the Heaviside operator as p. So what is this? If you think about it. So what is this derivative? This is a pretty straightforward. It's the product. So you can use the product rule. So it's the derivative of this times that, plus derivative of that times this. Right? So what is that? So it's y prime of t, u of t. Remember, the original y is two-sided. And then y of t, what's the derivative of delta of t? I'm sorry, derivative of the u of t. Freudian slip. Yeah, I gave you the answer. So what's the derivative of the u of t is the delta of t, right? So that's what it is, right? But this actually can be a little bit simplified a little bit more, right? Because this first part is what it is, y prime of t, u of t. But can I simplify the second part knowing that this is a delta? Do I need to really care about the value of this y of t at all times in this term? It's only one value that matters, right? Which is y0 delta of t. So it's the same thing. Now how about p squared of this thing, the second derivative? And you can actually continue doing this. I will just only do it up to the second. But you will see how it works out. So what is that? Well, it's the derivative of this, right? Which basically is what? So it's y double prime of t, u of t, plus then the derivative of this times that, which is basically y prime of t, delta of t, plus the derivative of, this is the constant, the derivative of that. What is the derivative of a delta? It's called a doublet. It's shown this way. Now, what is it? If you want to think about how you generated the delta, right? There are different ways to make the delta. You could make it alpha of a pulse, you could pulse, or something like that. You can also make it alpha of something like that. This is easier to see. Doesn't have to be that way. So what is the derivative of this? So the delta is basically where you make this narrower and make this higher so that the area of this thing remains constant, right? You could make it off of a step, a pulse. You could make it out of this like a triangular shape. You could make it out of a cosine. You can make out of a sinc function, which is the sine of x divided by x. There are different ways you can take a limit of something and make it into a delta, a Dirac delta. So let's assume that this is the way you generate it. This is probably the simplest way of doing that. So what is the derivative of this? So do you agree that it looks kind of like this? Well, same width as that, so it's a little bit wider, right? And as you make this narrower and as make this higher, this becomes obviously narrower and these two become larger. So the way actually a doublet is shown, the symbol for it is like this. That should make sense, that symbol. It's half of an arrow on this side and half of an arrow on the other side going in the opposite direction. If you cut the arrow along its their own direction in the middle. And then you flip one side. I mean, it's a notation, it's a symbol. But it should make sense. Symbols should make sense, generally. So what do I do with this? What is this useful for? Well, I can actually, and I can simplify this a little bit too. So This is y double prime of t, u of t, plus the second term can be simplified to what? Y prime of 0, right? Delta of t, plus y of 0, delta prime of t. So as you can probably, some of you probably have already noticed, you can see that these terms are appearing there. And this is how we incorporate the initial conditions, if you wanted to explicitly incorporate initial conditions into our solutions. And I'll show you an example of how that's done. Okay. And do you understand, any questions about the basic derivation of this thing so far? If not, let's do an example. So the example is, I put a second order example, but this is again generalizable. If you want to go to higher order, you have to keep calculating these things. And as you calculate them, you will get, y double prime of 0 delta of t plus y of 0 delta prime of t, delta double prime of t. So then you get y double prime of delta of t, y prime delta double prime, y 0 delta, and so on and so forth for higher order ones. Yeah? Okay, it's the derivative of the delta. Right? You can keep defining these things. But you will see, actually, you don't need to really do anything mathematical. I mean, you don't need to manipulate them directly. It's just a tool of tracking that thing. But these functions, you can just define. I mean, technically, even delta is not a function, technically. It's called it's more generalized class of mathematical objects, which is called a distribution. But again, we can treat them like functions, so that's fine. But it's a slightly different mathematical object. I mean, it's a more general mathematical function, but for all intents and purposes, for us, it doesn't matter. You can just think about a derivative of that, right? If I take the derivative of that, what do I get? If I were to differentiate this, I get a delta here, I get a giant delta down, and I get a delta up here, right? This is, well, giant meaning twice as large. So this would be then, as you start compressing them, it would be something that would look like a little bit of that, a little bit of that, and some of that. And you can keep doing that. I mean, whenever you are in doubt what it is, and that's why eventually it may make more sense to make these out of more smooth functions. Because then as you differentiate them, you will see that the derivatives are also smooth functions. And then when you look at them, they make more sense. Like when I tried from this to that. It was a continuous function that allowed me to go one step farther without getting into a delta. But then the second step got me into a delta, there's nothing wrong with it fundamentally. But there are different ways of dealing with that thing. But if you want to understand what's going on, sometimes it's easier to do it with smooth functions. But usually smooth functions are harder to manipulate analytically. So it's a trade-off. Yeah, it's fine. There's nothing fundamental there. Okay. Any other questions? No? Good? You're good? All right, so let's do a differential equation. So let's say the differential equation is y double prime plus 2y prime plus y equals 1. And let's say we are interested at t is greater than 0, and we have a y0, which is y of 0, the initial condition at time 0, for the value of y is 2. And then we have a y0 prime, which is y prime of 0 to be 1. So there are two initial, of course, this is a second order differential equation. You need two initial conditions to define a solution, right? Why do you need two initial conditions? Now, all of this should come together in your mind right now. Think about the order of the system, the number of independent degrees of freedom. When we looked at an RLC circuit, how many initial conditions did you need to define? That's the order of the system. The order of the system is second order. This is a second order system. Because the denominator of that system operator, which comes from this side going down to the other side, will be second order. And as such, it will have two roots, two poles, as we'll start calling them soon. And therefore, you need two initial conditions. There are 2 degrees of freedom in this system. There are 2 knobs that you can independently turn. Does that make sense? You look skeptical, Daniel. Okay. All right. Good. Okay. All right. Any questions? All right. So how do we solve this? So let's see how we solve this. So let's think about this. If I'm trying to solve this, there's one thing I'm going to do. I'm going to multiply both sides of it by u of t. Okay? So let's multiply both sides of it by u of t. Okay, now I'm going to run out of space. I've got to keep getting more microscopic. Yeah. Okay. All right. Sure. So we have these terms. Now, can I identify those terms in these? Can you see those terms that we have for the second order differential equation times multiplied by u of t by this unit step in these two things that we calculated? Right? You can see this and you can see that, right? So what this allows me to do is to express these two in terms of these, in terms of the one-sided function, minus these things that depend on the initial condition. So that's what we are going to be doing. And when I do that, it allows me to plug in the initial conditions into the thing and take these terms to the right-hand side and make them part of, and effectively make them and treat them like an input. So initial conditions and inputs in this viewpoint become more similar to each other. You don't treat them, it allows you to treat the initial conditions as some sort of inputs to the system, which is not that surprising, right? Because if you have a certain set of initial conditions, you can always set up your system by hitting it with the right input. That input may be a funny input. Just so you are funny in the sense that you may need to hit it with impulses and doublets and things of that sort. But there's a combination of these things that allows you, which is exactly what we're going to be calculating, to set it up in that state if you start from a zero state. So inputs are more general, if you will, than initial conditions. Because initial conditions are like one point-wise thing. But inputs are more broad. So inputs in this notion, in this way of thinking, are a superset of initial conditions. So anyway, philosophical. Let's get practical. Okay, so help me out. Help me write these terms in terms of the y plus of t, right? Because I have, and also there's a third one, which is here already, right? So I have all those three terms on the left-hand side here. Right? So I can express all those three terms in terms of these and the initial conditions. So help me out. So help me write the first term. Who's going to do it? Any volunteers? Should I volunteer somebody? I guess I should. I guess, Adiot, we can start from you. Start with this. So it's p squared of
y plus of t,
right,
minus y prime of t.
Y prime, y0 prime, which is the same thing, right?
Y0 prime
delta of t
plus
or
minus.
Minus, because these are basically moving to the other side.
Yeah, minus y0 doublet.
Delta prime of t doublet, yes, exactly. Yeah. And then what's the second term?
Then you have p of
2. There's a 2.
Okay, 2p of y plus.
2p of y plus of t.
Yeah, and then you subtract off y0 delta of t.
Yes, thank you. And then what else do I have?
And then it's just y plus.
Y plus, right? This last term is y plus of t itself.
Yeah.
And then on the right-hand side, I have what? Just u of t. Okay, now that's fine. There's one more thing I'm going to do. I'm going to write the right-hand side also as a function of delta, because we are expressing everything in terms of the delta, right? So if I wanted to write u of t in terms of a delta, what would I write? 1 over p delta. Yes. Thank you. Yes, Julie. Yes, you're not missing anything obvious. We are. You're making a good point. It was a mistake. Thank you.
You could also probably just rewrite like
Yes, yes. Now you're seeing where it's going, right? Before we do that though, I mean, I'm going to express all of those other terms in terms of deltas and p's, but before I do that, I'm going to take all these non-y plus terms to the right-hand side. This is, if you want to think about it in a different analogy, right? These three, right, the left-hand side of this equation are the genes. These are the inherited stuff of the system. The right-hand side is the acquired stuff. It's the effect of the environment on the system, right? So these are the more intrinsic, and these are more extrinsic. So you want to treat these initial conditions as extrinsic stuff, which is kind of right? I mean, you know, where you're born and who your parents are and all those things are also initial conditions, right, for you. Anyway, so let's keep these here. So now I can also simplify the left-hand side. Aditya, do you want to continue with that? So if I keep these three, can you help me simplify, capture all three of them in one term?
Like just the y plus terms?
Yes, just like some sort of a term up front. So it could be a p squared plus 2p plus 1 of y plus of t. And then I move everything else to the other side. So I get, and I can actually even plug these numbers in, right? Because these are, now I know what these initial conditions are. These are initial conditions that I already have, right? Here. So what is y prime? So this is 1, so I get a delta of t from this guy. I get what? I get a 2 delta prime of t here. Check my math, make sure I don't make a mistake. And then I get another 2, is it 4? Yeah, so it's 4. No. Delta of t. And then I have that thing that was already there, right? 1 over p delta of t. And this is all nice and good. I can actually simplify this a little bit more too. I can write this also in terms of delta of t, right? How can I write doublet in terms of delta of t? P delta of t by definition, right? So I'll just write this as p delta of t. So now everything is in terms of delta of t. So can you help me write the right-hand side in a similar form as something operating on the delta of t?
So you would have 1 over p.
Start with this.
Okay, sure. 2p plus 5 plus 1.
1 over p. Yes?
What about y0?
No, I use these two.
Oh, okay.
I basically plug the values in there. y0 and y0 prime, I just plug the 1 and the 2 in the equation. Yeah, good question. That's why they disappeared. Yes. Any other questions? No? All right. So now I have these two, right? So all I need to do is just essentially write I can write y of t, y plus of t, right? Y plus of t is just this operator divided by this operator operating on delta of t. So that produces y plus of t. Now, we already know how to deal with these things. I can simplify it a little bit. I can multiply it by p to get it into a more familiar form. And I can factor this, right? What's the factorization for this should be trivial, hopefully. P plus 1 squared. And then this becomes 2p squared plus 5p plus 1 on delta of t. So there's one thing left, right? Before I can use the catalog of solutions, which is what? Partial fraction expansion, right? So y plus of t, now we kind of do a partial fraction expansion. It's something over p plus 1 plus or minus something plus p plus 1 squared. Or let's start with that. So what's the k for p? What is the coefficient for p? How did we calculate it? We multiply this by p, which basically means that you eliminate this and set the value to the root of p, which is 0. So if you set p to 0, what is the value of this thing? 1. So this is 1. Then we multiply, if for this guy, we multiply it by that squared and set it to p equal to -1. What do you get? So you get 2 minus 5, -3 plus 1, -2 divided by -1 is 2. And then to calculate the last one, what do? Whatever we had, we need to differentiate it with respect to p and then set it to p equals 0, right? So again, this is eliminated. You differentiate this thing with respect to p. So what that thing is 2p plus 5 plus 1 over p, right? If you just eliminate that, right? So what is the derivative of this thing? It's 2, this is 0, 2 minus 1 over p squared. And we set p to -1. What do I get? What do we get? What is this for -1? P equal -1? 1. So that's my partial fraction expansion. So if I ask you what is y of t, which would be which would be equal for y of t for t greater than 0 would be equal to y plus of t for t equals 0, t greater than 0, not equal to, greater than 0. What is it going to be? Use the catalog and tell me the answer. I guess maybe next in line. Go ahead. U of t. What is p plus 1 squared? Oh, I think we missed one, but that's okay. We've already done this, right? This is t e to the negative. So these are t e to the negative t u of t. And what's the last one? E to the negative t u of t. So you see that, I mean, you can also write it as like 1 minus, whatever, like you can write it as 1 plus e to the negative t plus 2t e to the negative t, all of t, that times u of t. You can write it as 1 plus e to the negative t plus 2t e to the negative t u of t. Does this make sense? So you solve this equation with that initial condition. And what you're really doing is that, look, this is the initial condition. This is the input that would produce that initial condition in the system, that would induce it instantaneously at t equals 0. So you can see that the singularity functions are pretty powerful, because you can set up the system, you can take the system from one state to a completely different state instantaneously. It's like time travel. It really is time travel. And if you say, how's this time travel? Okay. What is time travel? Think about the state of every single elementary particle in every single atom, in every single molecule, in every single thing, right, in the universe. They have a certain velocity, and if you think about it that deterministically, which is what we are thinking about right now, not worry about quantum mechanical aspect of it, but just think about it classically. If I know all the positions and all the momentums, right, in x and y and z, and if I also know what they are at a different point in time, if I instantaneously change all these states, all these variables that are necessary to define what state it is in, all the initial all the positions and all the momentums, instantaneously from one position to another one, I have done time travel. Essentially, if I could store the state of universe at this instant, if I had enough power to take everything and bring it back to the state much later, I've time traveled to this point. If I freeze the state of universe here for 100 million years, in this exact state it is, and let it go, nothing would have happened, and we would have noticed nothing. Because every process has stopped. So this is exactly the same thing. So the initial condition, these kind of inputs take it from one state to another state. And when you talk about state space, which we won't do in this class, but later on when you talk about state space, which is another way of thinking about these problems, in a more advanced way of thinking about it, you will see how this applies. All right, any questions? Yes?
How would you apply this to circuits where...
You could do the same thing with circuits, right? So think about, for example, let me give you a simple example. Let's say you have an RC circuit. And let's say you have an initial condition on the capacitor. Let's say you want to have 1 volt initial condition. Let's say this is a 1 farad capacitor. Right? If I hit it with an impulse of current at t equals 0, an impulse with a magnitude of 1 coulomb, well, the area of 1 coulomb, more accurately, what happens? That impulse, that current will go through where? The capacitor or the resistor? Will go through the capacitor, right? Because all of it will go through the capacitor. Because if it goes through the resistor, its voltage will instantaneously go to infinity, right? Because at that point you have infinite current. But if it goes through the capacitor, it just raises its voltage. So instantaneously, it shifts its voltage from 0 to 1 volt. So it's as if I've set it up with a 1 volt initial condition. And of course, this is a simple example. You can make it more and more complex. You can define different kinds of current sources and voltage sources in different parts of the circuit that do this. Or you can do it through the input, through a combination of things that will switch the state of different things in different ways. And that would also be possible. Yeah. In the back first and in the front.
So what would a derivative with like y prime of 0 correspond to in a second order system with initial conditions? Like
This?
Yeah.
Yeah.
No, sorry, like y 0 prime?
This. What would it correspond to? Okay, so there are different ways. So it depends again what you're trying to do. For example, it depends on what you define as variables. So let's make a second order system. Okay. So if I am talking in terms of the voltages, right? The currents, so the voltages, let's say I'm trying to write an equation. The equation will have 3 terms, three of these currents in terms of these voltages, right? So think about it. What are those terms? There's a proportional term here, right? So let's say this voltage is called V of t. So this current is 1 over R V of t. What is this current? So so you know the relationship is I is C dV dt, right? So it's C P V or CP dV dt, right? And what is this current? L over, no, 1 over LP, well, yeah. 1 over LP V, right? So the two initial conditions are really, you can see it's this one and that one, the derivative. So the voltage of this thing and the current of that thing would be the two initial conditions associated with those. So it's exactly the same thing. If I give you the initial voltage of this and the initial current of that, you can get the same thing. All right. Any other questions? Yes, you had one. Sorry.
So for when you did the table lookup for
Mm-hmm.
over p plus 1 squared,
Right.
is it just generally true that t to the n e to the negative rt would be 1 over p plus r to the n?
Yeah, we derived this. We did that, right? I mean, yeah, I think we did that. So yes, that's true. Yes. So there's an n factorial thing, but yes, it's t to the m over m factorial e to the negative. Okay. Any other questions? Right, good. Okay, so let's take a quick break.